So now I'm going to walk you through how I approached question one in the problem set, and we'll start with question 1.1. So we are given this question says use ggplot in R to plot the function over the domain x is an element uh, of the set from -5 to 5. Um, so we are then given this function. So where f of x is equal to um, x when x is less than 0, and x squared when x is greater than 0. So right away, what pops out at me, just a few like mental notes to help me problem solve moving forward, is I know there's two functions within this function, and that really tells me that I am probably going to have to use an if else statement in my code when coding the function. Um, and we'll get to that later um, because we have a binary outcome. So the other thing that pops out at me is this right here. So we're given the domain of x needs to be within the set of -5 to 5. So somewhere along the data generating process, we're going to need to restrict our x to that set. And the third thing that I take away from this question stem is that we got to use ggplot. So those are the main three things that will kind of shape how I am going to be approaching this. So the first thing that I do here is I'm going to generate a vector called x of 10,000 equally spaced values in the domain of -5 to 5. So the way I'm going to do that is I am going to run this seq function, which stands for sequence, and I'm going to use -5 as my starting value. I'm going to use 5 as my ending value, and I'm going to tell it that I want the length of this sequence to be 10,000. So it's going to generate 10,000 values that are equally spaced between -5 to 5. So I call that vector x, and I'm going to run that now. And we can see it pops up here. So before we move forward to solving the rest of the question, I wanted to do a quick refresher on what an if-else statement is, because we're going to need to be using it to solve this question. So when would you use an if-else function? So it is best practice to use the if-else if you want to test one condition that has a binary outcome. So basically, if the condition meets the outcome, or if the whatever we're passing through the condition is true, we're going to return one thing. If it's false, we're going to return another thing. And those are the only two outcomes. So in the upcoming question, we need to test one condition. So is x less than 0? And it does have a binary outcome. So either we're going to calculate x or x squared. So the syntax for an if-else statement is as follows. So first you have your condition that you want to test. So in this case, we're going to say, is x less than 0? So if that condition is true, if the value that r is being fed is less than 0, then this is what we're going to want it to perform. And that will be just returning X in this case. And the third condition is what R performs when your condition is false. So this is basically like the else part of the statement. So if your condition is not true, this is what it's going to return for everything else. So moving forward to actually setting up the function, what I did here is I created a function called function of X right here. So what it does is it's going to take in a given vector of X that I created earlier. That's stored right here in the environment. And I'm going to pass it through this function. So each of these 10,000 values is first it's gonna iterate through this condition, right? So this condition is just asking, is X less than 0? So if X is less than 0, we're gonna output this. So we're just gonna return X unchanged. So if your condition is true, i.e. X is less than 0, output X. That's what it's going to do. And then if our condition is false, so in this case, X is greater than or equal to 0, that's the else part of the statement, we're going to output X squared, which is also equivalent to X times X. So in your code, you could also have this, and that would also yield the same output. So once we have the function down, so we're going to run this, we then proceed to the third part of this is the ggplot. Now we need to graph this. So one way of doing that is to use geomeline. And geomeline is a function within ggplot, which makes a bunch of little lines in between each of your data points. So you're going to have like 10,000 little lines here, and this will make your curve appear very smooth. In comparison, if you have like 10 data points, your curve will appear very rigid. So the bigger your sample size is, the smoother your curve will appear. So what I did here was first I ran the function. I passed X through my function of X, and I got this output of f underscore X. And I've annotated this code, which will be shared in an RMD, so you guys can go through and independently look through the code and be able to play around with it. So now you see in my environment, I have this vector here and this output vector here. So the next thing that I'm going to do here is I'm going to create a data frame or a tibble, which is what I'll do in this case. And that'll just allow me to store the data all together. So I'm going to run this and I'm going to create this tibble, right? So here, I'm going to do a sanity check, and I'm actually going to look through what my tibble consists of. So now that I am inside my tibble, which is called data X, I want to perform a quick little sanity check just to make sure my outputs and inputs align with what I want my function to do. This is always a good practice, just so you can kind of troubleshoot things before you get too far along, when then you don't know what went wrong with your function or where it went wrong. So what I'm looking at here is I went down to around 5,000 because that's like the midpoint of my 10,000 observations, because I knew that around here, this is where my function would transition from being less than 0 to greater than 0. So everything that's less than 0, you can see that all of these x inputs are returning the same thing for the outputs. So the function of x is returning these. And just wanted to note that these are equivalent values. It's just that this is now in scientific notation and this is not in scientific notation, but they're equivalent values. And then here, the key thing is now that this is even minutely greater than 0, the function already took the square. So it took this multiplied by itself and outputted this. And that's what I wanted to check. So the function looks like it's working. So now it's time to graph it. So what I'm going to do here is I'm going to use ggplot to graph this. So one way of doing this is to use the geom line function, right? So I'm going to indicate that geom line. Right, so what we need to do here is we are going to start our ggplot. We are going to specify what data we're going to be using, and we're going to use data underscore x. And then we're also going to specify what our independent and dependent variables are. So we use this aesthetics function to do that. So that will always be your second argument within ggplot. Your first one's your data, the second one's your aesthetics. So we are going to say that we just want x to be our x, and then we want our y to be our f underscore x. Because that makes most sense, since x is our independent, what we plug in, and f of x is our output, which is our dependent variable. So now we're going to start this geom line function that I was alluding to up here. And this will basically make, like I said, a bunch of lines and really make a smooth curve between your 10,000 points. And I set the color to purple just so you can visualize it more, and I increase the thickness. So the size argument increases the thickness just for visibility purposes. I titled my graph the function of x using geom line, and I added these labels. So I'll have x, which is also the input on the x-axis, f of x, which is the output on the y-axis. And then I added this theme just because it gives a nice, clean, minimalistic look to your ggplot once you output it. So I'm going to go ahead and run that code. And this is our output. So we can see here is everything below x equals 0, right? We see that this is a linear line, which looks like x equals x, or f of x equals x, sorry. And here now we kind of see this parabola, which is what we want to see. So we can now tell that everything greater than 0, we are now, or greater than or equal to 0, is now getting squared. So we're done with that part. Everything looks good. And once again, we just use the geom line function within ggplot to get that done. So now I'm going to show you a second way to do the same thing. And that's using the geom function, which is also within the ggplot package. So geom underscore function allows you to directly plot your mathematical function. So we can kind of skip all the steps that we did for creating a tibble and having like this over here, we can just skip that. So what we do here is we're gonna first start a ggplot. So R knows that this following code is we're trying to graph something in ggplot. I set the x axes limit. I set their boundaries from -5 to 5 because that's the domain that we're mapping this on. And this is the geom function. So the key difference here is instead of just indicating your color and your size, what I'm doing here is I'm indicating this right here. So this argument is called fun because it's so much fun. No, actually, it's fun for function. So I just put the name of our function in here, so the function of x, and then I specified the color and the size just like I did up above. And all of this is just the same code, copy and paste from up above. So the only thing I really changed was I took out this whole statement. I just took that out, and then I replaced this with this part with geom function, and then I added this argument. So that's all I did. And let's see what we get here. And now we get the same thing. We get this nice smooth curve where our values below of x is below 0 are this nice linear f of x equals to x function. And then you start seeing this parabolic shape once again when x is greater than 0, greater than or equal to 0. And we did this with the geom function. And one thing I did want to point out is see here we have just a smooth shape. We have no little dashes, none of that here. And in contrast here, you see you have these little like white little dashes that are in this graph. So this is telling you that geom line once again takes discrete like length values and this basically draws lines from each data point to each other. So that's what this is showing. So this is just another cool way of doing the same thing. And Alejandro has stressed in this class that there's a lot of different ways to do things in art. He just wants us to be like empowered to be able to figure out how we can solve the questions that they're asking. So moving forward to question 1.2. So now what the question is asking is this, or it's saying is this is a one-to-one function. Plot the inverse function f to the -1 power, which just indicates that this is an inverse, over the domain of y is an element of -5 to 25 of this set from -5 to 25. So just want to do a quick refresher on what an inverse of a function is. So an inverse basically just wants you to rearrange your equations to be in the form of x equals instead of y equals. So originally they gave us y equals x for or f of x equals x. We're just going to use y equals x just for simplicity here, is equal to just y is equal to x for any value that's less than 0. So the inverse of this is simply x equals y because they're equivalent values. You don't really have to do any algebra or anything like that to rearrange these things. For the second part of this function, for values that are greater than or equal to 0, we have this original function, which is y equals x squared. And to get the inverse of that is we need to take the square root of y. So I took the square root of y, and now we have x by itself on the left-hand side. So these are the inverse functions that we will be using moving forward to answer this question. So the key, I think, to also, dismantling this question is your y values are now your inputs. So your y values are your inputs, and your outputs will now be a function of y. So I just wanted to make note of that before moving forward, because this might be a point of confusion. So the first thing we're going to do is we're going to generate a vector. This is like the exact same step as I did with the previous question. I am generating a vector y of 10,000 equally spaced values in the domain of -5 to 25. And what I'm doing here is, once again, I'm utilizing this seq function, which generates this sequence. So I'm going to run that. And there we go. It popped up in here in the environment. And I am now going to set up my function. So I'm going to call this the function of y, set a function of x. And my only input here is just going to be y. And I'm going to pass this vector through this function. So I'm setting this up in the exact same way that I did in the previous question. I'm also using an ifelse statement. And the first condition that I am checking for, or the only condition I'm checking for, is y less than 0? So if y is indeed less than 0, if that's true, we're just going to output y. So that's the first argument, or the second argument. And then for this third argument, I am taking the square root of y if y is not greater than 0. So if y is greater than or equal to 0, this is what it's going to do, and that's what it's going to output. And this logic is the exact same as we did with the previous question. So now I made this function. So now let's run the function. So I'm going to pass y through the function now, and I'm going to assign it to f underscore y. So these values are basically like f of y, and they're going to print out in the environment here. And basically, what we have here is we see this in the environment now, and I am now going to do the exact same thing as I did up above, and I'm going to create a Tibble. So let's run that, and let's take a look at what our data looks like. So once again, I'm going to scroll down to about halfway through here. Perfect. So, oh, 1 second. That is, There we go. Because I changed the set. This is now ranging from -5 to 25, so it's not going to, so the zero value is not going to be evenly spaced in between. So what we're looking at here is for values that are less than zero, we're just going to output that same value. So for every input y, we're just going to output our f of y is also just going to be y. And then what we have here is values greater than zero. We can see that they are now, the square root of this value is getting taken and it's getting pumped out over here as the output. So perfect, our sanity check is complete here and we can proceed to the next step. So now that we know our function works, let's graph this using geomeline right here. So all my code is exactly the same as I did with the first part of this question. So only differences here is I replaced data underscore x with data underscore y because I'm now using this new Tibble. And my new input value or my new independent variable is y, and my dependent variable is now f underscore y. And everything else here is the same. I just changed the labels appropriately and the title. So let's run that. Perfect. So what we're seeing here is this nice linear line again. So we're just outputting exactly what we put in for values that are less than zero. And for everything else, we're now seeing this curve that represents something that's being like a square root is being taken. So that's exactly what we want to see. And that looks good. So now let's do the same thing, only we're going to implement geom function again. And once again, really the only differences here is that I didn't indicate the data set that I'm using here. And I also didn't indicate what my independent and dependent variables are. So I just removed this stuff from here. And then instead of geom line, I use geom function here. And I added this argument right here. So fun, which stands for function, and I input function of y here. So now it's going to give us this nice curve, which literally just maps the function itself. So we're not generating any data. We don't need to generate any data because this function, geom function, will just generate the function itself, essentially. So once again, we see that this is nice and smooth, no little discrete lines. And we see that this has these little lines. And both these things accomplish the same thing, basically, and answer the question. So both of these are a good way to tackle question one. So now I'm going to go through question three. So the question here asks or poses that let A and B denote any two subsets of the full set of all possible universes omega. So in part one, it's saying if I know the probability of A, the probability of B, and the probability of A union B, how can I figure out the probability of A intersect B? Hint, draw a picture. So how I approach this question, right, is I know that there is an equation that kind of ties all of these variables together. And the way I like to think about it is whenever I'm given a bunch of different probabilities or a bunch of different variables, I try to figure out, okay, is there one equation that can tie all of these things together? Because then if there is, I can just do some algebra and move some things around to solve for the other. So what I did here is exactly that. So we were given in lecture, we were given this equation, this first one right here. So this equation is the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersect B. So the way we were kind of told why this equation works is because if you take this whole probability of A, I indicated that this is purple over here, and you take this whole probability of B and you add them together, you're basically adding this part, this A probability of A intersect B twice. So you need to subtract one of those out to get the union, which would just be this area right around here, right? Without counting this 2 times. So this equation intuitively also makes sense. So what I did was I added the probability of A intersect B to both sides, and then I got this equation. So the probability of A union B plus the probability of A intersect B is equal to the probability of A plus the probability of B. So then to isolate this, I subtracted the probability of A union B from both sides, and I was able to rearrange everything and solve for our P in the probability of A intersect B, which was what the question was asking. So we're solving just for this probability right here. So there we have it. Now we have solved for this. So if you, whatever probabilities you have, if we know this, this, and this, we can just plug and chug into these 3 probabilities and we will get our intersect. Okay, so now let's walk through question 2, question 3.2. So question asks, when is the probability of A given B equal to the probability of B given A? So the way I approach this is that we know that this is possible when the probability of event A is equal to the probability of event B. So the reason I came up with this is because if we write everything out in probability notation, we see that the probability of B given A is equal to the probability of A intersect B is equal to this divided by the probability of A. And conversely, the probability of A given B is equal to the probability of A intersect B as it is up here. And the only difference is now that it's over P, the probability of B. So if we know that this part and this part are equal in both equations, the only other way intuitively to make the probability of B given A equal to the probability of A given B is for the probability of A and for the probability of B to be equivalent. So I drew out an example. say we're given that the probability of the intersect of A and B is 0.2, and the probability of each of these events, probability of A and probability of B, are both equal to 0.4. We will then plug this 0.2 into both of the numerators of both these equations, and these respective probabilities into the denominators. And we will see that these probabilities will be equal to one another. So that's just like a little proof to show that the probability of B given A is equal to the probability of A given B when these two events are equal to the probability of these two events are equal to each other. Okay, so now let's get to part 3 of question 3. So the question asks, if A is some subset of B, what can you say about the probability of A relative to the probability of B? So the first thing I kind of thought about when I saw this question was I wanted to draw a picture because I wanted to visualize how the probabilities could look. So if we know that the probability of, or that A is some subset of B, that means that the probability of A needs to be less than or equal to the probability of B. So we can make this circle bigger for the probability of A. We can make it smaller as long as it's contained, like within these bounds. That will be accurate. So what I deduced from this was that if we have the probability, if the probability of A is some subset of the probability of B, then the probability of A is less than or equal to the probability of B. So that was my final answer. So yeah. So going to question 4 now. So we get this excerpt and it asks us to list at least 3 things that we want to model as a random variable. So I read through this passage and I just really picked out 3 things that like represent one random variable, something that can be counted, or the probability of something occurring. So when I was going through this, right, I read this, I'll read it out loud. So we estimated change in the risk of asthma-related emergency room visits related to thunderstorm asthma events in Minneapolis-St. Paul, in the Minneapolis-St. Paul metropolitan area over the years 2007 to 2018. So at first, I was honestly a little bit tripped up because I thought the risk of asthma-related emergency room visits could be modeled as a random variable. And then as I thought about it a little bit more deeply, I realized that asthma-related emergency room visits by themselves can just be a random variable. It can be counted. So the number of asthma-related emergency room visits. So that was the key to me choosing that as one of my random variables. Then I continued reading. I read that, so we defined thunderstorm asthma events as daily occurrences of 2 or more lightning strikes during high pollen periods, interpolating weather and pollen monitor data and modeling lightning counts. So kind of all of this around what I have boxed here, the thunderstorm asthma events. This is what I chose as my random variable. This is just explaining how they defined this random variable here. So what they're really trying to get at is thunderstorm asthma events. Once again, something else that can be counted. And then this last one I thought was kind of the simplest one to pinpoint out of here because it straight up says lightning counts. So this can also be counted. So these were my 3 random variables, and I just wrote them down verbatim for my answer for question 4. So now we can get to part 5 of this. So we're given this depiction here. So the question asks, for the random variables x and y shown below, how does the probability of x being greater than a compare to the probability of y being greater than a? So the way I went about thinking about this, right, is what we really care about is everything above this line, above A. So we want the probability here of X and the probability here of Y. So I drew a picture here, and hopefully this will help kind of understand how I figured this out. So we know that these 2 functions intersect at the same point, right? And when they intersect, they both also cross over this like threshold of A. So they both become greater than A at the same time. And really the key here is if you look at the pre-images of X and the pre-images of Y, which I drew in here, they're the same. And by looking at the lengths of these pre-images and visualizing that they're the same, we can then argue and say that the probability of X being greater than A and the probability of Y being greater than A are equivalent because their pre-images are the same length. As Alejandro kind of depicted in his lectures. So basically what I have here is all of that just written in words. Just to reiterate, I said the probability of the probability of X being greater than A is equal to the probability of Y being greater than A because the length of the pre-images of the pre-image of X and the pre-image of Y are equivalent as depicted right here in this picture. Furthermore, we know that X and Y both intersect with A and cross over to X is greater than A and Y is greater than A, respectively at the same time point. So that is my explanation for this question. And over here, before we delve into part 6, I wanted to just quickly give a refresher about what Tibbles are and why we use them. So Tibbles are used to create a more flexible and faster versions of data frames. So they essentially do the same exact thing as data frames, only on steroids. So that's really all you need to know for what a tibble is. And then I just provided some brief syntax as to like how to create a tibble. So you would just write tibble, and then you would name your columns. This could be column 1, column 2, column 3, column 4, and then like column ends. You can put in as many columns as you want, and then you would just like insert whatever you want here. So this could be like your sequence from, let's say, 0 to 1, and you'll set the length being 100. So you could do that, and then here you can say like column 1, because now we already have this one made. We can say column 1, times 2, and then here we could say column 1 squared, or something like that. So you can really do anything with these. Once you make a column, you can kind of do like whatever functions you want in here. So I just wanted to like quickly reiterate that before we hop in to answering the question. So going to problem 6 now, 6.1, let's look at what the question is here. So we're given that let omega be in some set of between 0 and 1, and let's define a random variable. So they gave us this function xw equals w squared. So we're going to call this w omega, as Alejandro's been referring to in his lectures. So it tells us that it wants us to use sampling in R to approximately compute the probability that x is between 0 and 2, and then that x is between or 0.2 and 0.3, and then that x is between 0.9 and 1. So it wants us to do these two events separately. So what I did here was, first thing I did was I created a tibble, just as I was talking about. I called this tibble sampling 1 of 1, because this is the first sampling I'm doing here. So so this will basically just output as a tibble out in the data frame, so then we can like look at it later. So I generated our omega, so I just made a sequence of numbers that are evenly spaced from 0 to 1, because we were told that this omega needs to be between 0 and 1. And I generated 1,000 numbers that are evenly spaced between 0 and 1. And then we were also given that this function, this x, needs to be omega squared. So here I squared this omega and set it equal to x. And then we were also told here that we want this x value to be between 0.2 and 0.3. So I created another column called inset. So that was kind of the same nomenclature that Alejandro used in his lectures. And I set these conditions. So if x is greater than or equal to 0.2 and if x is less than or equal to 0.3. So that will kind of make sure that we're evaluating that is x inside or in between these two values. So what this is doing, which I think is kind of like a fundamental thing to understand, is that what we're really doing is we're testing whether these values are in this set or not. So if we look at the Tibble, this is going to return either a true or a false. So if we run this code and create this Tibble, we'll go here to this sampling. We'll see that these are false. And for values that lie inside of the set of 0.2 to 0.3, these will be true. So everything that lies outside of that set will be false, and everything that lies within it will be true. So this is important to know because in the subsequent steps, we're basically going to be counting how many true values there are to help guide us in calculating the probability out of the total values that we have in this entire table, basically how many observations we have. So moving forward, to actually calculate the probability, so I'm calling on this table that I created, sampling _1 _1, and I am running this count function onto here. And the reason I have this dplyr and then : in front of it is just because sometimes there's a lot of different count functions, and sometimes they get masked in our if you have other packages installed or loaded. So I just had this in front of it just so it basically uses the proper count function that we are intending to use. And basically, like I said, this is going to count the number of truths that were inside in this inset value in this column. So then after that, where this code here is going to create another column, basically, and which is going to give us the probability of x being in the set. So let's run that. And there you go. So we counted the number of truths. And I guess this also counts the number of falses. And we are given 101 truths, which means out of a data set out of 1,000, the probability of getting a value of x within the set of 0.2 to 0.3 is 0.101. Okay, so now going to see evaluate this part now, the only thing that I'm going to change, and right here I've elucidated the differences in the code that I'm changing, are that I'm naming the Tibble something else. I'm calling it sampling 1 _ 2 because I'm generating a slightly different sample. And I am now I have changed this right here. So before I had my set being 0.2 to 0.3, and now my set is 0.9 to 1. So everything else stayed the same other than this part, and this part, because I am now calling this data frame or Tibble that I created. So I'm just going to run that whole thing, and that will also give me the number of trues and the number of falses as well as their probability. So what we have here is the probability that are any values of x, the probability of our function x lying between this set here from 0.9 to 1 is 0.052. So moving on to part 2 of question 6, let's see what they wanted us to do here. So they want us to repeat the above. However, they want us to substitute this function now in for x. So the way that I approach this is I basically copy and paste my code from right here. I copy and pasted this code, and I made these following changes. I changed the mathematical formula for x, for the column x, to being 1 minus omega squared instead of omega squared. So that's right here. I also changed the name of the Tibble to sampling to 1 because now I'm working on a different question. I'm generating a different Tibble. So I changed the name just for organizational purposes. And then I also changed the set that I'm testing because I am now testing this set instead of this one. So after I made those changes, all the code is the same. Once again, the only lines that are parts that are different is this, this, and this, and this. So I run that, and we get the same exact probability that we got in our first question. So that is the correct answer, and that was how we got there. So now let's repeat all of this, only we need to change the set. So moving forward, what you can do is just copy this code, paste it into this code chunk, change the name of the Tibble. So I changed this to sampling to _2_2. And I kept this the same because we're using the same formula. And all I did was change this. And then I changed this line. Well, actually, we can remove that. That's not necessary here. And yeah, so the only changes are here for the names and what's in this set. So I'll move that over here and let's run that. So that gave us the same probability as we actually got for this question. And that just shows you that how these functions are interrelated with one another based on what we covered in week 3 is that their distributions are similar to each other, although their functions themselves may be different. So that was what this question was really trying to get at and elude for us moving through the following week of content. So now on to the last question, which I personally thought was the most complicated question of this problem set. Definitely was a head scratcher for me. So the question asks us to write our function that takes as inputs a number A, a number B, and a function X that takes a number omega that's an element between of 0 and 1. So, and returns a number which uses sampling to output an approximation of the probability that X is an element of A and B. So there's a lot of stuff in this question. It's a fairly loaded one. However, I'll do my best to kind of dissect this and share my approach to writing this function. So what I did here is I first made this function. I just called it prob underscore sampling to stand for probability sampling. And the function to write one, this is always the first thing you have to do. So you need to write function. It'll turn this in this color, and you would do the parentheses, and then you would put your arguments in here. So I actually added this argument n in here, which was totally unnecessary. However, that's just how I did my function. This was just so I can insert whatever sample size I wanted, and then the function would spit out a probability at the end. So that doesn't really complicate things that much. So the key thing is here is that I have a number A here, or this would be B, and then F is going to represent my function. So one thing I did want to note here is that these like variables, they're objects in R, so they can really represent anything. Like it could be a number, it could be a factor, it could be a character, it could be a function itself. So this right here is going to be our function moving forward. So that will help answer this question. So then what I did here is I set a seed. I set the seed to, let's set it to 241 just because we're in 241. And the reason I'm setting the seed is so if you guys go and reproduce my code exactly as is, you guys will get the same exact probability. So what we're doing here moving forward is I'm generating an omega, and what we've done in the previous questions is we've always generated an omega being like a sequence of numbers ranging from like -5 to 5, negative or 5 to 25. However, what we're doing here is I am generating a random uniform distribution. And as part of this distribution, we need to set our sample size. That's why I put this here. This was just unique to the function I was writing. However, there's different ways you could do this. And then I set the minimum being 0 and the maximum being 1. So this part of the question, since I'm generating a random uniform distribution, this will address this part right here. It'll generate, I'll have an omega that's an element of this set. So that answers that part of the question. And here I have a function. So this, I'm inputting this function. And when I specify this function in my inputs, it will pass omega through it and generate this this X. So that'll take care of this stuff. And this last piece to the puzzle is I'm just running a probability calculation to basically see is my X in between A and B. And if it's true, I'm summing those values that are true. I'm counting those values that are true, and then I'm dividing them by n, which is our total sample size. So the sample size is whatever I input. So that will calculate the probability, and then this function will then return the probability. So it will return the probability that my generated X function is in between whatever A and B I set it to. So let's try it with an example. So here I'm running the function. I set my A value to being 0.4, my B value being 0.7, and then my sample size here is this is just 1 with 5 zeros after it. So this is the same as this 1, 2, 3, 4, 5. That's the same as 100,000. So then the key here is I put in a function to here. So I am putting this function of X, right? I'm just telling it that this is a function of X. And then this is the actual math that it performs right here. So I'm going to run that. So it's going to take X to the 4th power and then multiply it by 2. So I'm going to run that. Oh, sorry. I need to run this function because it's not in my environment yet. And then now I'm going to run this. And voila. So this gives me the probability that my values of X will be between the A that I gave it, the B that I gave it, with this sample size, and passing these omegas that I generated through this random uniform distribution through this mathematical function. So I know that this may be a lot to kind of take in right now. So I've further dissected this code and really annotated every step of this code. So you guys can go through and really understand what each piece of this code is doing one by one. So then when you're faced with a similar question, you can kind of refer back to this and maybe extract certain pieces and then like repurpose it for whatever other questions may come up in the course. So here, what I really just wanted to show is this step right here. This step just sets up the function and its inputs. So I called this something different. I called this probability sampling underscore 1, just because I wanted to show like the reproducibility of it. So here I'm just naming the function. Here I'm setting A, which is the minimum value of our like given set. B is the maximum value of our given set. N is the sample size. And then F is the mathematical function that you will input, right? So I also wrote here that this does not need to be a numerical value. So like these three are all numbers, but this is a function. Like you do not need to always input a number into a function. You can always put in a character or a function itself. So now that we're done with that part, let's get into the body of the function. So this is where the function starts. This is what your computer processes once you give your function its inputs, right? So we have this opening bracket here, right? So this opening bracket indicates where the function begins processing. Let's set the seed again to 241. And this seed, really what it does is it's just for reproducibility purposes. So once again, if you guys copy and paste this code, run it yourselves, you guys will get the same exact answer for the probability every single time. And that's like a good way to like check your work if you're working in groups and study groups, stuff like that, to make sure you guys are getting the same answers. Here, I'm running this random uniform distribution which I pass my sample size through. I have it set for the minimum of being 0 and the maximum of being 1. And again, this part right here, that's generating this omega, the reason I did it this way is so it answers this part of the question right here. A function x that takes a number omega that's an element of 0 between 0 and 1. So that's why I have that there by design. So this generates omega. This will generate 1,000 or 100,000 values of omega, whatever my sample size n. In this case, it was 100,000. It'll generate 100,000 omegas. And then it'll take these 100,000 omegas and it'll run them through whatever function I put in f. So here I had this function. I'm just indicating that it's a function of x here. And then this is the math that I want it to perform. So this is the same thing as saying 2 times omega to the 4th power. So this is equivalent. So this is what R is performing right here in this step to generate X. So now once I have generated X by passing our omega values through here and calculating this, I am now running this function to calculate the probability that our X is between A and B. So once I have that, I'm just going to output, return this probability of P, and it's going to print out into the console. And then this is the closing bracket, which indicates where the function stops processing. So now let's test this. I am putting in the same exact values, right? So I'm just saying that I'm setting A to 0.4, setting B to 0.7. My sample size is 100,000, and I have, and then this is the function that I'm putting in. So let's run this all again, and let's see what we get. So, all right, awesome. It spit out the same exact value because we changed the seed. If we, just for demonstration purposes, let's say I'll change the seed, let's just say to like 247, right? Let's change it in both, 247. Now let's run this whole thing. So now it gives me a different probability because the seed is different, and it's generating different random distribution as a result. I'll run this here. So now this function will also generate the same random uniform distribution, and I get the same probability. So that's very neat. And you can tinker with this, right? You can change any of these inputs. You can make this like 2 to 4. You can increase the sample size, and you can change this function to whatever you want, really. And it will give you your probability. So I think this is pretty neat. Thank you for watching my explainer video on assignment 2. And if any of you guys ever have any questions with R, please book an appointment with me or Jessica. We're our tech support team. We're here to help, and we'll try to assist you in any way that we can. So thank you so much, and happy coding.